Welcome to the 27th lecture for Physics 4B. In this lecture, we demonstrate some applications of driven AC circuits. We demonstrate the usefulness of the complex impedances we introduced in the last lecture by using them to analyze the series LRC circuit, also done in the textbook with phasor impedances, as well as a version of the LRC circuit with the inductor and the capacitor in parallel, which is not done in the textbook due to the limitations in applying phasor impedances. In the second half of this lecture, we look at the power dissipated in AC circuits, illustrating calculations that can be facilitated with the complex impedances. We leave the AC circuits here, leaving additional examples of AC circuits to homework. There's much more that can be done with the use of complex impedances, but not enough time in our semester to explore them fully. So this would be another example of driven LRC circuit. Now, as you look at this and try to figure out how to do that using phasors, you can't really, or you can't do it easily, because in order to do this analysis, what you need is you need to add these elements in parallel. And you haven't been given rule to how to add phasors in parallel. Because I think you can, I figured out that rule at some point, but that was so complicated that it wasn't worth using. So that's the limitation of your textbook approach. It'll just limit you to whatever circuit elements are in series, because it's not versatile enough to handle anything other than that. And what I'd like to show you in this lecture in the next, 10-15 minutes is, let me first redo what the textbook has already done with the series LRC circuit, because that'll give us a way to compare our answers to see if the approach I'm using is actually yielding the exact same answer textbook has already gotten for LRC circuit. And then we'll go on from there to analyze these new circuits and see how their behavior is different. I think I want this lecture topic to be LRC Circuit Analysis, plural, with complex impedances. So let me give you a quick reminder of something that was covered in lecture, complex impedances. So if you imagine this circuit element, resistor. So what impedance is it's a kind of generalized idea of resistance. The motivation for impedance, as you see it in lecture, it comes from trying to recover the simple form of Ohm's law in the more complicated cases. So this impedance being the generalized idea of a resistance, when it comes to the impedance of a resistor, well, that's just resistance. It's the idea of itself being itself. Now, when you have other circuit elements, like capacitor, they have different impedances. Impedance of a capacitor is 1 over imaginary number times omega, angular frequency at which you are driving the circuit, times C. And the impedance of an inductor is imaginary number times omega times L. So these are impedances to drive it or intuit it. You'll have to work through some situations. I've done that in the other lectures. I'll just use this as a given thing, that we are given complex impedances. And so this is being generalized idea of resistance. It means whenever you have these elements, you can add them like you add resistors. So for example, if you had them just in series, resistance, capacitance, and inductance. And let's say you are trying to get some results out of this circuit, so you connect it to an AC power source, one that provides fixed amplitude voltage. So I might, in the realm of complex impedances, I might describe this voltage source as being a function of time with some amplitude of V0, and then the complex part, e to the I omega t. If I'm trying to do this without complex numbers, I might be describing this e to the I omega t as a cosine of omega t, and so on. So let's imagine you have these three elements connected in series. And I just said you can add these elements like you add the resistors. So what that means is if you're trying to combine them all into a black box, and you're trying to think of what is the equivalent impedance of these three elements added together, well, you add them like resistors in series. So you say, okay, that's my resistance, done, plus the impedance of the capacitance, 1 over I omega c, plus the impedance of inductor, I omega L. And that's your equivalent impedance. And the whole motivation for introducing impedance being trying to recover the simple form of Ohm's law, you can say from Ohm's law, the voltage across all three circuit elements is given by their equivalent impedance times the current as a function of time. So I can imagine taking this, solving for current. Current as a function of time is the voltage, which is V naught e to the I omega t, divided by the equivalent resistance, which I wrote up here. R plus 1 over I omega c plus I omega L. And I guess you could leave it here, except it's not much of an analysis. It doesn't add much of an insight. So let's just separate out a little bit. So we're gonna separate out this e to the I omega t dependence, which I'll find a way to handle. So I have the coefficients of V naught divided by, and let me do this as well. So I see this nested fraction, and I never liked nested fractions. That kind of mess with my visual. So I'm going to try to get rid of this nested fraction. The way to do it would be to multiply top and bottom separately by I omega c, by I omega c. On the numerator, you get what you get. On the denominator, this is expected to cancel this out so that you don't have any more nested fractions. So let's do that. So let's write down what's going to be on the numerator. So that would be V naught times I omega c divided by, let me be careful here. So I'm multiplying I omega c to every single term. So it'll be I omega c times r plus, this will become 1. That was the whole point. And then finally the last term here, it'll be minus, because of I squared, and then omega squared times LC, minus omega squared LC. All right, as you stare at it, it might not be quite informative. Let me just make a little bit of space here. Like, what does that even mean? It is a little bit helpful to separate out different parts. There's this time-dependent part, e to the I omega t, which I'm going to ignore for now. And for the expression for current, let me write this fraction this way. So we have V naught times I omega c divided by, let me write the real part first. So I think this combined is the real part. 1 minus omega squared LC plus I omega RC. So as you look at this expression, you can get some things just by staring at the expression. One thing that you can get is, one question that you can actually answer by staring at the expression is the question, at what angular frequency is current maximized? And if you're thinking, this is such a complicated expression, how could you get that by simply staring at it? I focus on the part where I see potential for cancellation. So if I'm trying to maximize current, I'm trying to minimize the denominator. And here, other than making omega 0, I can't do anything there. But in this term, there's a value of omega that's not 0 that'll make this real part 0. That value being omega equal to square root of 1 over LC. So if you plug that in there, square it, LC cancels out, you get 1, 1 minus 1, hey, that's a 0. So this is the resonance frequency. That's something you can get just by staring at it. The rest of it, it'll need a bit of a mathematical sophistication, which is, I want to look at it this way. So, I have this complex number, and I need to explain a little bit of tricks about dealing with the complex numbers. So, looking at this number as a whole, I can think of this like it's a complex number g, lowercase g. And when you have a complex number, you have two different ways of representing it. You can represent it in the Cartesian form, a plus I times b, or you can represent it in the polar form. Let me not use r because that's going to get confusing. Lowercase r times some magnitude times complex exponential e to the I phi. And you can see that it's going to take quite a bit of work to even to get this to look something like a plus ib. I have to rationalize the fraction and separate that. I could do it, and it's not really going anywhere that way. So let me just not go here at all. And just deal with this expression. Let's imagine I'm trying to write out this complex number. V naught I omega c divided by 1 minus omega squared LC plus I omega RC. I'm trying to write this in this way. I want to write it out so that the complex phase factor is pulled out, and what it's multiplying to will be basically the absolute value of the complex number. And this might actually sound like even more complicated thing. How do you calculate that? So this is the trick about working with the complex numbers. Imagine doing this calculation just because you can. Product of complex conjugation of this complex number times itself. And this complex conjugation, the operation for it is really simple. It's obtained by replacing wherever you see I with minus I. And if you have any complex variables, you have to also conjugate it. But R and phi are both going to be real. So here, the G conjugate would be R times e to the minus I phi. This is a simple calculation. Let's do it. When you do it, you have R times e to the minus I phi times R times e to the I phi. You get R times R squared. You get e to the minus I phi times e to the I phi. They just cancel out. So this product here gives you the magnitude squared. So when I want to calculate this, the really simple operation to calculate that is, okay, let me write this out. That's going to be equal to square root of the complex conjugate of this number. It takes some steps, but it's simple to write it out. Let me write out V naught times minus I omega c divided by 1 minus omega squared LC, and then minus I omega RC. That's the complex conjugate. That times the original complex number. V naught I omega c divided by 1 minus omega squared LC plus I omega RC. And then square root all of that. That'll give us that magnitude. So let's go through that algebra. It's a little bit tedious, but it'll be well worth it. Let's write it out. So and it's actually not that hard. So it's a square root of, I have V naught squared. and minus I times I gives me plus 1. Alright, so I don't have to do anything there. I have omega squared, this is squared. Oh, this is going to get pulled out of square root. Okay, that's being divided by, the denominator is a little more complicated. Let me do this easy part first. I have real part times real part. I can kind of treat this as one unit. Let me just write it out. 1 minus omega squared LC squared. Okay, and I have cross terms that will cancel. Like this times that plus, or so let me highlight it. This times that plus this times this, they will cancel each other because one product was done with the plus sign, the other product is done with the minus sign. So those cross terms will cancel. I won't even write them down because they will just cancel. The only remaining part I have to deal with is the imaginary part multiplied to imaginary part. So minus I times I, that gives me plus 1, and then omega squared, r squared, c squared. Good? I guess I can simplify this a little bit, maybe. So let me do this. I'm going to do two operations at the same time. So I'm going to pull out v naught squared. So I'll have that. Or pull it out of the square root, so it'll just become v naught. And then what I'm going to do is I'm going to multiply top and bottom within the square root thing by 1 over omega squared c squared. I think that'll eventually end up looking a little bit simpler. So this term, out of this term, I have, let me write it out. I have square root of omega squared c squared gets cancelled out when I do multiplying top and bottom by 1 over omega squared c squared. So this will be r squared. And then the remaining term here, I could write it as plus. So this is being squared. When I bring this inside here, it becomes division by omega c. So it'll be 1 over omega c minus 1 factor of omega cancels. So omega L and then c cancels, squared. So this is the result. This is the result here. So let's kind of track our way back here. Let me just erase this to make room. So tracking ourselves back here. For our original expression for the current that we are still trying to write out, we can say that, okay, that current is, there's some time dependent part, and there will be some this complex phase part that we'll just leave alone for now. And then for the kind of the quantity that determines the magnitude, we can now say, copying and pasting this, that this will give you the magnitude of the current. So if someone was asking, question like, what is the IRMS? Then I can say, this top part being, that's like VRMS, or it'll be proportional to VRMS. I can say, I can write that in terms of VRMS by dividing it by this factor here. All these other things, they in computing something like root mean square quantity, they will disappear. They will become 1. So this will be VRMS divided by square root of r squared plus 1 over omega c minus omega L squared. Now let's compare this result with what your textbook derives. So looking at series RLC circuit, they do all this stuff. Great. Nothing wrong with that. So phase factor they did, we skipped it. We'll leave it skipped. We are just using this to kind of check the validity of this approach, and then we'll do the phase factor for the other circuit we'll analyze. So so we have, okay, I naught is, there it is. And this is how your textbook wrote it. And you can kind of see hints of that here, especially in this rewritten form. And this is G here, it's that. And did they ever plug in the actual quantities? Okay, they didn't, but they did cover XL. The impedance of an inductor was omega L minus 1 over the impedance of capacitor is 1 over omega C. and that's this. The minus being swapped around doesn't matter because we are squaring it anyway. So yeah, this is the same formula that's in the textbook. So you can analyze a series RLC circuit this way, and the benefit of this approach, using complex impedance to analyze a circuit like a series LRC circuit that even your textbook covers, is that I didn't have to draw any drawing. This was just algebra. So once you get used to the way of doing complex algebra, then this is so much easier. One. Two, you didn't actually lose any information, like what your textbook was covering with the phasor diagrams. All that information is still here. Like if you represent these in the complex plane, you will get the equivalent version of a representation using phasor diagrams. Now, what we are gonna do next 5 to 10 minutes, is really the advantage of this approach. It's highly adaptable. You can use this to not just analyze a series LRC circuit, which again your textbook already does. I've simply redone it in a different way. But let's say you had a slightly different circuit. So let me take this beginning part of it, and we'll just change it around a little bit. Instead of these circuit elements being in series, let's say you move it around a little bit. So let's say your resistor will be in series with the power supply. Let me actually put it here. But your capacitor and inductor, they won't be in series with this. Instead, you are going to put capacitor and inductor in parallel with each other. So here's the capacitor, and here's the inductor. So equivalent impedance won't be this anymore. We'll have to think of a way to rewrite it. But our setup still remains kind of similar, in the sense that with the use of complex impedances, generalized version of resistance, you can still have a form of Ohm's law that relates the voltage and the current linearly through the impedance, the generalized resistance. And if you are given this circuit and trying to analyze it using phasors, it's going to be complicated. I tried it once and I don't know that I can do it correctly again. The difficult part is adding the capacitor and inductor in parallel. I think doing that using phasor diagram is non-trivial. And so what I'm going to do is I'm going to use impedances. So if these two had been resistors, I know how to add them. They are in parallel. I know how to add resistors in parallel. So I would say, okay, 1 over equivalent impedance of L and C, that in reciprocals, that's going to add to 1 over impedance of capacitor plus 1 over impedance of inductor. Okay. Let's write that out. So I have 1 over equivalent impedance of just the inductor and capacitor is 1 over I omega C is just I omega C plus 1 over I omega L is 1 over I omega L. All right, there's some symmetry here. And just combine the fractions, same denominator, I omega L. And then here, multiply top and bottom by I omega L. That's what I'm imagining doing. I omega L, top it by I omega L. I times I, that's minus 1. So minus, and then omega squared LC. And then I still have 1 plus 1. Okay, that expression. Now I can just take the reciprocal for the equivalent to impedance. That's I omega L. And let me write the 1 first so that I don't have to lead with a negative sign. So that's the equivalent impedance of that block. For the total equivalent impedance, I simply add it to the impedance of the resistor, or the resistance. So the overall impedance, the equivalent impedance, is the resistance plus I omega L divided by 1 minus omega squared LC. Okay, so so with this expression, we can say this. We can say that our so solving for current in that expression, the current in this circuit looks like the voltage, which is V naught e to the I omega t divided by the equivalent impedance R plus I omega L over 1 minus omega squared LC. All right. So let's imagine we are interested in the amplitude of the current. So we are imagining rewriting this into this form, where this is equal to some I naught times e to the I omega t plus times potentially a phase factor, and we'll say this is gonna be the real quantity. So in trying to get that number, we can take this as my complex number g, and if we calculate square root of g complex conjugate times itself, that'll give me a number such that, let me write it out this way, the complex number g can be expressed as this real number times a complex phase factor. So if I compute this, that'll give me this amplitude of the current. So let's calculate that. We are calculating the absolute value of V naught. This is how actually absolute value is defined in the complex number algebra. You so you know with the real numbers, you might have taken the number, squared it, and taken square root. Like that's one way to define the algorithm for taking the absolute value. And when you are doing that with a complex number, you do something similar. You just go through an extra step of taking the complex conjugate instead of squaring. So this absolute value is going to be square root of, let's write the complex conjugate first. That's this quantity, just with all the i's replaced by minus I. It'll be V naught divided by R plus minus I omega L divided by 1 minus omega squared LC. That number times the original complex number itself, V naught divided by R plus I omega L over 1 minus omega squared LC. I have a sense this will actually look pretty simple. So a lot of the multiplication here is simple. You get, V naught times V naught, so that's V naught squared. So the remaining part is working out this complex expression times this complex expression. And one thing that'll simplify is, again, when you do, so you get R times R, so that'll give you R squared. And when you multiply this with that, and then add that to this multiplied by that, they will add up to 0. Those cross terms just vanish. So with that great simplification, I can just write this out. So I have a V naught squared square rooted. So let me just write V naught on the numerator. And in the denominator, I'll still square root. And I have R squared from the two real parts multiplying together. And the cross terms, they cancel out. So I'm just going to have the imaginary part multiplied to the other imaginary part. Minus I times I is plus 1. I have plus omega squared L squared divided by this thing squared. Square root. Alright, can I simplify this a little? Let's take a look. So let's see. I don't think there's much more you would gain by trying to algebraically simplify this. Let me highlight this. So before we saw this resonance frequency of omega is the square root of 1 over LC. In the before circuit with the series circuit, this is where you saw the current being at maximum. Now, in this circuit, you won't see that. This quantity of I naught, when you plug this in, you won't see this becoming maximum. But you will see something interesting. So let's just try plugging in this resonance frequency. and see what happens. So when I plug this in, so let's just write out the expression. I have V naught divided by square root of r squared plus, okay, plugging that in, square it. So L squared will cancel out. So I'll have, actually L squared, it'll, so when I square it, I get 1 over LC. So it just cancels one factor of L. So it'll actually have L divided by C divided by, I have 1 minus, plugging that in, I have 1 over LC, those cancel, so I have 1 squared. Oh, so this is what I see. This combination here, this is approaching 0, which makes this entire number approach infinity, which means this r squared is kind of irrelevant. It's insignificant, doesn't count in anything. And this entire quantity here, representing I naught, equals to 0. So what on resonance behavior means for this circuit is that the current through the circuit will approach 0 on that resonance frequency. And you can kind of follow through the consequences of what that means. That means if the current flowing through the circuit approaches 0 at that frequency, then the voltage drop across the resistor, that voltage drop will go to 0, which means all of this voltage being provided, that will be measured across this combination only. So you can look at the resonance for this circuit in this way, that's the frequency at which you will measure the maximum voltage across this circuit element. And so one might wonder, okay, that's interesting. This is a different circuit, behaves in a different way. So given that this is a lower division class, and we don't have to cover everything in circuits, we actually don't have time to cover everything in circuits. So given that both this and this gives you resonance behaviors, what's the benefit of working with this circuit, let's say in a lab setting, rather than working with this circuit? Like, why not this circuit? Why not stick with it? Why not stick with what the textbook covers? Experimentally, the one big thing that makes a difference is the role of the resistor. So here, the resonance behavior shows up in current. So you might be, and in order to measure the current, you do need to measure the current voltage across the resistor to calculate the current that way. So in terms of kind of measuring things, you want the resistor to be reasonably large. However, when you think in terms of power dissipation, so resistor gives you what's called damping. So it's what it's what makes things oscillate not as well. So, and the amount of damping you have in an oscillator, that determines the sharpness of resonance peak. Your textbook has a picture of it. So if you look at the textbook, resonance in an AC circuit, they have this picture of it. So this is the resonance, and it has some width. And this width, how broad that width is, how narrow that width is, that's associated with how much damping, how much power dissipation there is. And when that R is large, that makes this width broader. So when you're working with that, do they have expression for? Yeah, they talk about the Q factor, quality factor. And you see it here. The quality factor becomes lower when the R is greater. And what that means is when you are working with a series LRC circuit, you have to balance these two practical things. That in order to be able to measure that resonance behavior and give it proper interpretation, you want this R to be reasonably large. But as this R gets larger, it'll make your Q factor, quality factor, lower. So the kind of resonance you see won't be as sharply picked. It'll be more kind of less of a sharp resonance. And That's a trade-off you're just gonna have to have with this. And that's a trade-off that you don't have to have in the LRC circuit that you saw me draw below. So in this circuit, when you go through the same similar analysis your textbook does, um, so I guess actually I can do the analysis here. So when I have this expression for I naught, and the quantity that I'll be measuring for my resonance behavior will be this delta V. And let's say when I do that measurement, I expect that delta V to depend on the driving angular frequency in something like this. Some kind of resonance. And we'll expect to see this peak at omega equals 1 over square root of LC. And at that resonance, I'll actually see the full power supply voltage V naught. And I might think about, okay, at half maximum, at the value where I have a V naught over 2, what would be the frequency that's away from this resonance? What would be this delta omega? And I can look at it here. So in terms of the current, what that would mean is this current would have to be halfway between the maximum current, which would correspond to the V naught over R, and the minimum current, which would correspond to 0. So it would have to be V naught over 2R. That's what we are looking for in terms of the current that's flowing through the circuit. That will give me this condition. So let's look at it. I have V naught equal to V naught, so I can cancel those out. So I'm setting this equal to 2R and see what kind of frequencies you get. So I have 2R is equal to square root of R squared plus omega squared L squared over 1 minus omega squared L C squared. Okay, so to get rid of square root, square both sides, 4R squared is equal to R squared plus omega squared L squared over 1 minus omega squared LC squared. And instead of doing this algebra by hand, let's use a Sage math. So let's declare some variables. We're going to be using R, and instead of omega, let me call it omega squared, because I want to treat this omega squared as like x. So actually, let me just define that as x, and I'll just put in x where I see omega squared. And I need L and I need a C. Okay, those are my variables, and my equation will be 4 times R squared is equal to R squared plus omega squared, which is x, times L squared divided by 1 minus omega squared, which is x, times L times C squared. Okay, that's my equation. I can solve for that equation for x, and it'll know to treat everything else as a known quantity. And I should get two solutions because, it's quadratic. And let's see, will it... It looks super complicated. So, but I think I can write it down and make some sense of it. So let's write down our omega squared. You get two solutions. I think I can write them both kind of together. I have 1/6 times 6, and then this R squared C plus L, and then this is what I'm looking at. I see this and this expressions are the same except for minus and plus here. So I'm gonna write plus minus square root of 12 CLR squared plus L squared, all of that divided by this denominator. So C squared LR squared. So as you look at that, I think there's let me do a little bit of a human simplification so that it's easier for me to kind of attach meanings to things. I think this 6 is kind of redundant. Let me absorb it into the thing. Then I have for the first term, I got so 6's cancel out, and for the first term let me simplify with the denominator as I write it down. R squared cancels out with that. C cancels out 1 of the C squared, so I have 1 over LC as leading part of that omega squared expression. And then I have plus, let me write the second term. There's going to be some shift in frequency apparently. L's cancel, and I have 1 over 6 R squared C squared. Okay. Interesting. And finally, plus minus, and let me write this out. So 6 coming in. So I'm going to just write everything under square root. Then 6 being squared, 36. So that combined with the 12 will be... Actually, let me just write it out. It'll be 12 CL R squared plus L squared over, and then 6 squared, so 36. And then all these things are squared, so it'll be C to the 4th power, L squared, R to the 4th power. Yeah, and this is what I want you to mainly demonstrate. When you look at this, so this plus minus, this is basically what's giving you this right side and the left side of that delta omega. And as you look at that, look at this expression here and see how this behaves as R goes to infinity or as R goes to 0. Those are kind of two limiting behaviors that's useful to look at. And this whole combination of quantity goes to 0 as R goes to infinity, because you have this R to the 4th power in the denominator that overwhelms everything there. So as R goes to infinity, this thing that determines the width goes to 0, which means at larger resistance values, your resonance becomes more sharply peaked. That means your the Q factor, the quality factor increases with increasing resistance. And in a circuit, it's always easier to add more resistance. So if you can achieve a higher Q factor, sharper resonance by having a larger resistor, that's in practical terms kind of easier circuit to build and analyze. So this alternative circuit, which you can only analyze using complex impedance, it has that practical benefit that when you are building it in the lab with a real circuit, that you can use easier values of resistances to work with. Because as you use those larger resistances, your Q factor will increase. So you will see a more prominent resonance behavior. So this is a review of power dissipated in circuit. I guess what I really mean to say is not necessarily DC circuit, but maybe a more correct way to say it is register-only circuit. Things get more interesting when you have more than just two registers. And when I talk about AC circuits, there are really two parts that make a circuit AC circuit. The first thing is you need an AC power source. So what I mean by AC power source is a sinusoidal, and it can be a voltage or current source, but let me make it a voltage source since that's most common. So I needed some kind of power source, and I'm just gonna say my power source being represented with the complex numbers is going to be V naught times e to the I omega t. So AC circuit, it needs AC voltage source. That's the one thing that makes it AC. And technically, I can have this connected to just a resistor. And I mean, that nothing stops me from doing that. But this is not very interesting. So yeah, and this actually is revealing one of the things we have to be careful about whenever you are using complex numbers. I think I do mention this in the lectures. I don't know how much emphasis I place on it. It's basically the things you should be mindful of when you are using complex numbers or complex functions to help you with the calculation. So there are things that are okay to do with the complex numbers. So for example, things like addition, subtraction, derivatives, integrals, even scalar multiplication are all okay. What all these represent are linear. I think that's something that you will get a more detailed definition of when you take linear algebra covered in Math 3E. So let me just leave that there. These are all linear operations, even taking derivatives and integrals. And with these linear operations, certain relationship between the real and the imaginary part of a complex number is preserved, or they are transformed in a predictable, nice way that later on you can do things like taking the real part and get a number that you would have gotten if you didn't use complex number. So these are all okay things. It's quite a few, which is why using complex number is it's a good thing to do in AC circuit analysis. But what you have to be aware of is that there are things not okay with complex numbers. That certain operations that if you do, you are going to mess up the relationships, and then you will get a result like this, which is not actually correct. I mean, got some aspects of it correct, but it missed this whole offset that you should have gotten. And I guess I can list the two of them, which is function multiplication, and the other you can kind of guess, function division. Division is kind of a a kind of multiplication. So these things are, they will mess up certain things that are set up in a complex number. And these are examples of things that are not linear operation. You can kind of get that, if you have a function that's a function of x, and a function of x, let's say x. And if you do any of these, then this function will remain in the order of x. But if you do things like multiplication, then you get x squared. That's where it doesn't look linear. I will let Math 3 do more detailed, mathematically proper discussion of what linearity means and why function multiplication does not preserve linearity. So, and here's an illustration of how this can go wrong. Imagine you have a function, a complex function f with a real parameter t as an input. So it's a complex function. Technically, I could do it this way. I could represent it with the real part plus the complex part, or imaginary part, technically. And so for the purpose of this illustration, if there's a second complex function, which also has a real part and an imaginary part, sometimes doing this separation can be very complex, but imagine that it can be done in principle. Then in playing with these is where you can see what I mean by these are linear operations. If you do any of these, the real part and the imaginary part will stay separated. No amount of addition, subtraction, derivatives, integrals. Scalar multiplication is a tricky one because they can actually mix the complex and the or imaginary and the real part. So this is a, let me just point that out as somewhat more complicated one. So you can at least see for 1 through 4 how they are linear, and how if you took these complex functions, did addition, subtraction, derivatives, or integrals, and then just took the real part, then you can swap that order of operation and everything will be fine. But let me try doing function multiplication to show you how that all goes wrong. So when you do function multiplication, this is what you get. So multiply complex function t with complex function f with a complex function g. So this is the full algebra. You have to write out the whole thing, and there are potentially 4 terms here that I will get from this multiplication. Let me just try to quickly write them all out as quickly as I can. Plus ig complex part or imaginary part. Sorry, I tend to use complex as a synonym of imaginary, and that's not technically right. So I just need to write out these terms. G times or f times g. So that's one term here, fr times gr. That's fine. That's one of the terms I would have gotten as I'm doing just the regular real function multiplication. So I expect you to see this. That's perfectly fine. And let me do fr times ig complex. Then let me try to separate this out as I'm writing the terms. So I'm going to write the terms with the imaginary I in separately here. So I get fr times g complex, and the mixing of this concerns me a little, but you know what? It's in the imaginary part. Imaginary part, I'm going to throw it away later anyway, so maybe I don't care. Okay, let me keep going. I have IF complex times GR, so it has a factor of I again, and I get so plus F complex times GR, and both functions of time, and it's in the imaginary part that I'm going to throw it away later. So maybe it's fine. It's actually not fine, but maybe I'll say it's fine. And this final term is what gives me trouble. I have I fc times I gc. I squared is -1. So I get this minus f complex times g complex. So it's this term here that makes multiplication not work. So when I did this multiplication, there is this term that came from that imaginary part multiplying with the imaginary part that basically changed my real part from what it would have been without the imaginary part. So yeah, so function multiplication, not kosher, not okay thing to do when you are working with a complex number. There may be a very limited set of circumstances where you can, and scalar multiplication might be considered one of those. But in general, if you are multiplying a complex function with another complex function, you better know what it is you're doing. So going back here, so then how is using complex number in any way useful? I mean, this problem is not a complicated problem. I'm just simply calculating power and doing with just the register. I haven't even introduced the capacitors and inductors yet. So if I can do something as simple as computing power with just a register circuit, without first, so if I had done this, turn current into real part, the voltage into real part, and did a calculation that way, then I would have been fine. But
that seems like I then might as well just deal with the trigonometric functions. Why go through the trouble of introducing complex numbers? So there are certain circumstances where I really want to multiply functions together, and if I can't do that, then it feels like it's not worth using complex numbers. So let me show you what you can still get out of here while using complex numbers. So there's a very specific way in which you can do multiplication that will give you a very specific quantity. And you can do this multiplication in a very easy way. So you might have noticed that as I was talking about this calculation here, where I made sure everything to do with just the real function so that it's all correct, I was very quick to get to the average quantity here. And there's really two reasons. One is that average is really simple. It's constant quantity, it's easy, nice, good to work with. That's one. If it's easy and nice, I'm gonna consider using it. And two is a lot of times you're actually interested in the average quantity. Imagine like a power in your house. It's a 60 hertz AC circuit, but you don't really care about the 60 hertz oscillation, or I guess 120 hertz oscillation in power usage. At the end of the day, what you really care about is either total energy used or very closely related to total energy used. You are interested in average power consumption. So there are circumstances where what you really want, so I want to make sure I limit myself properly. That I'm not talking about a generic circumstance where you might want to multiply two complex functions together. Because if that's what you want to do, there isn't a general solution for that. That's just a limitation of using complex numbers. But you might have a circumstance in where, let's say, if you have a complex function f and you have a complex function g, and so they represent oscillatory quantities like this. Let me use the letters I'm already using. Let's say you are interested in so both of these v and I, they have their real counterpart. So the real counterparts v and I, let's say you are not necessarily interested in their direct product. With the real functions, you can calculate it, but let's say you don't really want that. What you really want is the average of this product, as in you want time average. So it's a function of time, and you want this product that's been averaged over time. So the precise mathematical definition of that average would be first to integrate that product as a function of time from 0 to some big time t. That's many multiples of the period, and then you divide it by 1 over t. This is all the summing up of the contributions, and then dividing it by t gives you the average. Let's say you're that's really the quantity that you're interested in. And you can see from the calculation that I did here that that average is actually pretty simple, because this cosine term, in the average, it's just going to get averaged out. If a t happens to be exactly one period or integer multiple of a period, it becomes exactly that. But if a t is simply a quantity that's much larger than a period, then you can argue through how the integral of cosine omega t over the time period is some number between -1 and 1. And when you divide it by 1 over t, it becomes vanishingly small for t going to infinity. So really the only term that doesn't vanish is 1 over 2. The integral gives a factor of t that gets canceled out, and the average simply becomes the magnitudes of v naught times I naught divided by 2. And since the result with the real number is so simple, watching that, I hope that there's a way to do an equivalent calculation using purely complex functions without ever referring to the real version of it. And there is. And this is how you do that calculation. You do the calculation by doing this. One of the functions, you are going to need to take a complex conjugate. So let me erase all of them. So if you compute this quantity specifically, so let me choose current to take the complex conjugate of. So for the current complex function, I'm going to be dealing with a complex conjugate. And as a quick review reminder, this is what I mean by complex conjugate. So let's say I have some complex number, or let's say I have this, and I want the complex conjugate of this quantity. To obtain complex conjugate, all you do is take the imaginary I and change it with a minus I. So this complex conjugate here will be e to the minus I theta, where theta is a real parameter. If theta is not, then that gets conjugate sign too. Or splitting it out like this, it becomes cosine of theta minus I sine theta. Once again, if I can treat theta as a real parameter. If it's complex parameter, then it gets its own conjugate sign too. So I have I, or I star, the complex conjugate of the current function. Let me multiply that with the voltage, the complex function. When I do this product is going to be, and I can show you specifically for this example that it is. And a claim I will make without proving, because proving it takes time, is that it's generally true whenever your complex functions are oscillatory in time like this. And what's generally true is, so this product will be equal to twice the time average of the product of the real version of these functions. So you saw me write down this time average before. This was equal to the magnitudes divided by 2. That was the time average. You saw it in the graphical form here, and you saw the algebraic version just a couple minutes ago. So I guess what I'm claiming with this statement here is when I do this product, it better come out to I naught times V naught. And let's see if it does. Let me write this portion out explicitly. So the I complex conjugate is going to be this. Or let me, for the sake of simplicity here, let me just replace this with the I naught. I mean, I know what it is in terms of V naught and R, but let's say I naught. So it's going to be I naught times e to the minus I omega t times V naught times e to the I omega t. And when you do this product, do the exponential algebra, you get I naught times V naught. And oh yeah, that's what I said I was going to get. So in this specific example, it worked out. Okay, and the claim I'm making is that this is going to be generally true whenever these are oscillatory functions of time like this. Then I guess if you're like me, I'm a bit of a contrarian, and whenever someone claims something, the very first thing I do is think of counterexamples, and that's what was distracting me. What was distracting me, which is a case which is not true in this case, but it's something that could be true in a different case. What if it's I naught e to the I 2 omega t? What if there was something that was forcing the current to somehow have double the frequency of voltage? Then I guess bit of a problem here is that, so when you do that calculation, I think you are going to get a number that it's not technically real. It is complex. I think if you do another time average with that, like if you do another time average, then it'll fix the issue that I'm gonna point out. So, you will end up with this quantity here, e to the minus I omega t. And if you were to do a time average, then the time average will actually turn out to be 0. And 0 is actually physically correct answer. Turns out if this has double the frequency, then some of the time you are dissipating positive power, some of the time you are dissipating negative power, which technically should mean power input, and those average out to 0. But if you don't average, then you have this complex number, and yeah, so let me not worry about that. I think make a more limited version of the claim that I think I was trying to make here, which would be, so I think let me limit my claim here so that later on you don't find a counterexample where you find what I'm saying is wrong. So let me just, because I think I can limit my claim and still make it be useful for our purposes here. So the limited version of claim will be this, where you are dealing with only a single function. So with a single function, you still have the same problem that I was pointing out about how you can't multiply a complex function to another complex function. So if you have, let's say, complex voltage source T, then what you would get with taking the real part of the complex function squared, what you get here is different from what you would get if you took the real part and then squared what you got there. That's different. Just to do basically the exact same calculation I did before. It's not the same. And with this limited context, this is the claim that I can make. So even with just a single function, you have trouble multiplying the function to itself. You can, yeah. But again, if the context is that maybe I'm not interested in the square of the function itself. So if what I'm interested, so this is the real version of the function. If what I'm interested in is the square of the function itself, as in what we would get if I had a v naught squared over r cosine, or that. So I guess that's cosine squared omega t. So if this actual function of time is what I'm interested in, then complex functions can help you get there correctly. But let's say I'm not actually interested in that. What I'm interested in is just an average over time, or just writing out explicitly just 1 over t integral from 0 to t over v of t squared dt. If that's what you're interested in, then the complex functions can help you get there, because I can say without any hesitation or counterexamples that work out that this quantity here is going to be equal to the quantity that I'm writing on the left-hand side. The complex function multiplied to complex conjugate of that function divided by 2. And you can see with the example I have up there, if I do this calculation, then so this is what it looks like. Kind of the same thing I did up before with the v naught e to the minus I omega t times v naught e to the I omega t. It's the same calculation I did before. Divided by 2. So it's a v naught squared over 2 e to the minus I omega t cancels out with e to the I omega t. The difference from what I did before is that because it's the same function to itself, there is no possibility of these two frequencies being different. So this complex factor is guaranteed to cancel out. And this is equal to the time average that you can get if you calculated that. And so and if you imagine taking this, multiplying by 1/r, that'll give you the average power dissipated. So there is a way to get to average power dissipated in AC circuit that uses only complex functions and very simple operations using complex functions only. So never dealing with anything more complicated than complex conjugate operation, which is just replacing I with a minus I, and simple products of complex numbers that can be worked out relatively simply algebraically. So this expression is what I'm going to be utilizing. In fact, probably the current version of that, because as I was saying at the beginning, what I prefer whenever I'm calculating power is to use this expression. And one upside here is that it's a function of, or it depends on single function of time only, I of t. And so it looks like it's going to work out. Yeah, so maybe I should do a couple examples. Yeah, so this was what I was starting out as a power dissipated in AC circuit, and I guess technically it's AC circuit, but it's a AC circuit that doesn't have all the interesting features of AC circuit because it's just resistor only. The time dependence of current is exactly the same as time dependence of voltage. So, I mean, okay, so there's time dependence, and it's a good practice to introduce operations with these new mathematical things. And after having done that, it's not quite an interesting setup because just resistor. What makes a AC circuit interesting is it's what earlier made the time-dependent circuits time-dependent, capacitors and inductors. Those circuit elements, by their definition, always involve some kind of time-dependent things, integral with respect to time or derivative with respect to time. So before, when we were trying to apply DC voltage, those elements introduce the time dependence. And with the AC circuit, where there's a sinusoidally driven power source, those components will also introduce interesting phenomena. Where I want to end with in about 30 minutes is discussion of something called the power factor. I think your textbook also talks about it too. And this is something to be aware of in engineering applications, and particularly in industrial settings where people are running, let's say, large motors. You're driving inductive loads that require large amounts of current. And if you are not careful, there's ways where you can be wasting a lot of power. So there are some considerations that people use, and I think there's a correction. Yeah, power factor correction of linear loads. Yeah. So I think this is what it's talking about. And it's the kind of thing that electrical engineers would consider. And that's where I want to end that in about 30 minutes or so. So let me build up the rest of discussion of power in AC circuit in this way. So we are still talking about power dissipated in AC circuit. Let me try this version first. I want to make it interesting, but I don't want to make it too interesting. Or, I want to try to keep it simple. So in an effort to keep it simple, I'm going to have a single component. And here, let me have a very unrealistic single component, which is a single inductor. It's not quite realistic to have. I think this was covered in one of your conceptual questions. And the reason I say just voltage source inductor circuit is unrealistic is that inductors bound to have some resistance in the wires and whatnot. But let's say we are living in theoretical world, and I can build a circuit. Maybe it's a superconducting wire. Um, so, so the idea of complex impedance introduced earlier makes this analysis super simple. So this inductor, it has impedance associated with it that's represented by I omega t. By the way, what I do is, for those of you who might be taking electrical engineering courses later, what we physicists do is usually somewhat different from what electrical engineers do, which is that I use lowercase I to mean imaginary number. And I never use it for current. When I mean current, I will be using capital I. In electrical engineering, I guess for some reason they use lowercase I for current often. So they would use that for to mean current and lowercase j to replace that. So that's a convention that you may see in the future. I'm not going to use that convention. My lowercase i's are imaginary numbers, and my uppercase i's are always current. So, okay. So I said the analysis of this was simple. And if you are, imagine applying Ohm's law, which says that current is voltage divided by resistance, and impedances work like resistances, then this current induced through this circuit should look like the time-dependent voltage divided by the impedance of the circuit. And that exactly gives you the answer. So let me just write it out here. It's so V naught divided by I omega t times e to the I omega t. Let me rewrite this a little bit, because I think written in this way, it's a little bit, doesn't bring out all the meanings here that's in a way that's really easy to see. So let me rewrite current as a complex function here. Let me write down all the real coefficients first. V naught over omega t. And I'm going to have e to the I omega t in the end. And let me do something about this 1 over I. So 1 over I is equal to minus I. To see that equality, you just multiply to I. Both of them will give you 1. Because I squared is minus 1 times minus is 1. 1 over I times I gives you 1. So 1 over I there, that's really minus I. But even that is a bit, it doesn't quite bring out the full meaning of this imaginary factor. So I want to write this in what appears to be unnecessarily complex way. I'm going to write it this way. E to the I 3 pi over 2. I mean, are they even equal to each other? Well, let's check. So use Euler's formula. This thing, expression, better be equal to cosine of 3 pi over 2 plus I sine of 3 pi over 2. Cosine, so, this is my thing. So pi is this, 3 pi over 2 is this angle. Oh yeah, cosine of that is 0. And sine of that is this component here, so minus 1. So yeah, so that is equal to 0 plus minus 1 times I, minus I. So I'm going to replace this number with that, e to the I 3 pi over 2. And you can see why I'm writing it into something that actually looks more complicated, because now I can do exponential algebra to combine these two exponential terms. So my final expression has this form of real coefficient that you can actually get easily by going through the same thing your textbook does, voltage divided by magnitude of impedance, times this complex exponential, which contains both the information about the time-dependent oscillation and here, for the first time today, phase factor. So it's going to look like e to the I omega t, that's the oscillating part, plus 3 pi over 2. That's the phase factor. Or I guess technically the way that's more commonly written is actually minus pi over 2. So this is phase factor, and this is what tells you that the current through the inductor, I think the correct term is it lags the voltage. But I always get those languages mixed up. What I never get mixed up is this mathematical expression, because that comes straight from Ohm's law. So, so this is the expression for the current through the circuit. It's out of phase. It's not. So when you plot the current and voltage through this circuit, this is what you're going to get. So let me imagine that I'm taking the real part of the voltage and the current function. So the voltage part will look like a cosine. It's gonna do something like this. And the current part, oh, I guess I better write this out. So it's a cosine of omega t minus pi over 2. And then there's the imaginary part that I'm throwing away. Let me rewrite this using cosine angle addition formula. It's a cosine of omega t times cosine of pi over 2. Oops, that's 0. So that's going to be, whole thing's going to be 0. Plus, because that's minus, sine of omega t times sine of pi over 2. This is 1. So sine of omega t. Oh, so the current will just look like, so if I plot the current, it'll just look like a sinusoidal thing. So, okay, something like that. So yeah, so the current is out of phase with the voltage. And I want you to talk about power dissipated in AC circuit, because this is where I think if you're simply following mathematical formalism, you can get lost, and meaning of the mathematical expressions isn't quite clear. So I think it's easier to start with the answer. So let me just start with the answer here for this particular question. The question being, what is the average power dissipated in a circuit? And that's something I can actually attempt to answer by using this representation here, because these are all real functions. So if I'm doing average over time, that's better give me average power in the circuit. And I hope as you consider these expressions, voltage goes as cosine of omega t, that the current goes as sine of omega t. That I hope you know enough trick to know that if I have cosine of omega t times sine of omega t, and I'm averaging this over long time, 0 to t, or 0 to capital T, 1 over t, that this whole quantity is going to be 0. There are ways to prove it, but let me just make that assertion. And you can kind of see it in the graph here. These two are not in phase, so you can see a portion here. So up to this portion here, your power is positive. And from here to here, your power is negative. Whatever that means, it could mean that you are putting power back into the energy source or whatever. And from here to here, negative times negative. So here your power is positive again, and you can kind of get intuitively from this graph that that positive and negative oscillating power expression, it's going to average out to 0, and it does. So that's the answer I want you to start from. That when you average power in a circuit like this, that average power consumption is 0. And I hope that makes intuitive sense, because this circuit contains no dissipative component. Inductor, when it's perfect, it only stores energy and releases energy, in the form of magnetic fields. But it only stores and releases energy. It never even though this expression that current, the complex current is voltage divided by Z, even though that looks like Ohm's law, certain aspect of Ohm's law isn't there. Because Ohm's law always relied on some kind of power dissipation in the element. But, inductor, it comes from Faraday's law, and it involves, power energy dissipation. It only involves transfer of energy from power source to the magnetic field in the inductor. So I hope when you get the answer that average power dissipated in this circuit is zero, that it makes intuitive sense. And this is where I want to caution you when you are, so knowing that correct answer, that I hope that knowledge of correct answer guides you as you apply, as you do further circuit analysis and as you answer certain questions. So let me imagine making this circuit a little bit more complicated, maybe in an attempt to model the inductor better, or maybe my inductor is a motor and I have long power transmission line and I'm interested in just the whole thing, transmission line plus the motor. What you do need to do that kind of modeling is to say, all right, instead of saying that this circuit has only one component that is the inductor, I need to have inductor and I need to have a resistor modeled. And in certain aspects, this is a super easy thing to modify our calculation for, and this is why I introduced the complex exponentials or the complex impedance. Because once I have a resistor, the resistor has some impedance, that's actually just a resistance. And these two elements, the impedances, they behave like resistances in almost many, well, in most cases, one exception being when you're dealing with the power. So in order to include this resistor in your analysis, all you have to treat this circuit as is, all right, so it's the two series component circuit. So I need to calculate my equivalent impedance. That's going to be sum of these two. So I omega, I wrote T there. It should have been I omega L. Inductance. So equivalent impedance is going to be impedance of the inductor plus impedance of the resistor, R. All right, that's my equivalent impedance, complex impedance. And my current will simply be application of this formula. My current as a function of time is going to be my time divided by impedance, the equivalent impedance. Oh, I guess not as a function of time. So it's going to be V naught e to the I omega t divided by this thing, R plus I omega L. And you can see that some aspect of this will be complicated, as in, so when I have a complex number like 1 over R plus I omega L, this is, I guess I can rationalize it. So I can rationalize it to rewrite it into this Cartesian form. And when I do that, I'll have this common factor that multiplies R squared plus omega squared L squared. And then I have this R minus I omega L. And so, I have this this times this as the real part, this times this as the imaginary part, and there's that Cartesian representation. And there's also this polar representation. And I'm just going to give you the expression without proving it. And the expression is this: 1 over square root of R squared plus omega squared L squared times, so this is the magnitude or absolute value of the complex number, times e to the phase factor. And I guess I can write down this much. The phase factor phi, it's given by tangent of phi, is the the ratio of the imaginary part of the complex number divided by the real part of the same complex number. So the expression for phi in a case like this, it's gonna be a little complicated. That's why I want to just write it as phi, knowing that I can always get what it is. So using this here, I can rewrite my current into this form, the magnitude or the amplitude of current oscillation, which is going to be V naught divided by square root of R squared plus omega squared L squared times, and this oscillatory portion will have a phase factor, e to the I omega t, and then it'll have this phi, plus phi. So I wrote it in such a way that, this phi is likely going to be negative, but I'm just adding phi here. So yeah, that's the expression for current as a function of time, and in some sense, there's nothing simpler. It's just all right. That's kind of the same thing I would have done if this were an resistor instead of an inductor. The only additional complication I had to go through dealt with a complex number, which is the price we pay for this being such a simple thing to analyze when you use complex exponentials and complex impedances. And you can even use this to do certain calculations. You can do this calculation. You can calculate power dissipated in resistor. That calculation I can still perfectly do in the AC circuit context. And all I have to do is this. So from our earlier discussion, really the only thing I can get at is the average power. The instantaneous power takes too much effort. I'm not going to do that. But I can get to the average power dissipated in resistor. And that's going to have this form, that average power is going to be the average of the current squared times the resistance, because this is constant. And with the complex exponentials here, this can be written in a very simple way. That's simply the complex function conjugate times the complex function itself divided by 2. That's what gives you the time average. Multiply that to R. And let me just finish out this calculation. I have this expression for the current. You know that when I do conjugate times the complex function, this exponential here is going to disappear. So this product here is simply going to be the coefficient squared. So it's going to be V naught squared over, so R squared plus omega squared L squared. And then I have the remaining factors of R over 2. So that's the power dissipated in resistor. And all right, I guess one way you can convince yourself is if you imagine the inductance going to 0 or omega going to 0, both of which will make inductor like a wire. When you do that, this should reduce down to V naught squared over 2R, and that's what you would expect, V naught squared over R from before, and the factor of 1/2 from averaging cosine squared omega t. So this is a sensible expression. And yeah, you can do that, and that's perfectly fine. That'll give you the right answer, and there's nothing for you to worry about. The thing that if you tried to do would give you an expression that really should give you a pause, and it's this, which is, let's say imagine a version of you or version of this class where I forgot to go through this discussion, and I gave you a homework assignment like that, and so now you're computing the power dissipated in inductor. Let me attempt to do that. So I say, all right, power dissipated in inductor, and I somehow remember or think that, I can have this formula here and just use the impedance of the inductor instead of resistance. And if I do it correctly, it'll look like this. I'm going to be writing down the power average is equal to, all right, I need the current squared average times the impedance of the inductor. So I know how to handle this. I know how to deal with the complex numbers. And so I do complex conjugate times complex function itself, divided by 2, times the impedance. That's going to be I, not omega t, but omega L, so not dependent on time. That's fine. And when you finish calculation, this is what you're going to get. V naught squared over r squared plus omega squared L squared times I omega L. And I hope if you ever do this, that you are observant enough to notice this I. And I hope that makes you worry, because power is supposed to be a real quantity. And so, here you are not supposed to need to do anything like taking the real part. Like, it was already expected to be real. But because the impedance of inductor is imaginary, the calculation here doesn't give you a real quantity. And what this is telling you is that, or I guess you can pretend that you needed to take real power. But I think what's more better, less to take away from this is that inductor doesn't dissipate power. So there's no such a thing as power dissipated in inductor. Inductor doesn't dissipate power. You can only really calculate power dissipated in resistor. And when you calculate that, you do it the normal way you would if you're just dealing with a DC circuit, just with some details about complex numbers that you have learned. If someone asks you how much power is dissipated in inductor, you say 0, without even needing to calculate it. And if someone asks you what's the power dissipated in capacitor, you say 0. You don't even need to calculate it. And if you were to attempt a calculation like this, then then, then this imaginary thing will hopefully tip you off that something's wrong here. You look up whatever reference you need to realize that, oh, there's no such thing as power dissipated in inductor. If there's a power dissipated in real motor, then it's dissipated in the portion that's modeled as resistance of the motor. So what I want you to end here is kind of a scenario, and a scenario that can help us figure something out. And I guess I need to construct this correctly. So let's see. So I want you to imagine a device that consists almost entirely of something that has inductance, like a motor. I think motor is what I want you to think about. And I want you to imagine that this resistance is relatively small. That's much smaller compared to omega L. And the motor typically needs certain amount of voltage, V naught, to operate. Okay. The scenario I'm trying to build up here is this. So right now with this circuit, this is the expression that you have for power dissipated. Let me let's see. Let me rewrite it this way. So I'm going to rewrite it as V naught squared over R times I basically, or 2R times, what I've basically done is multiply top and bottom by 1 over R squared. So 1 over R squared cancels out one factor of R and leaves a factor of R here. That's what I have there. And multiplying the denominator here by 1 over R squared will give me 1 over 1 plus omega squared L squared over R squared. Okay. Yeah, I think that's let's see. Is that yeah, I think that's probably a good starting place. So just to have some sense of numbers, what I want you to kind of assume is that V naught is relatively large and R is relatively small. And with the stipulation, I hope you see that this quantity here is then it's then relatively large if this well, I mean, this coefficient is a relatively large quantity, and thing that causes you a bit of an issue is this omega squared L squared. And I think how I want to specify that is that do I want it to be relatively small? Let me just make this easy for myself and just to say this omega L is equal to R, because I keep wanting this to be small, but let me just say omega L is equal to R. Under that scenario, this numerical factor is 1/2. And what you see here is that there's a fairly large power dissipation in this resistance R, which is only incidental to this setup. So this whole device, it mostly has inductance, and this R could be it could be the resistance of the wire. And so there's a lot of power that's wasted on the wire. And this is the scenario where the power factor is what the Wikipedia article was describing as when power factor is high. And what I want to describe now is the modification that can be made to the circuit to remedy this situation, that a lot of power is being dissipated in the register. And it really comes from the fact that this circuit draws more current than it needs to. So this is how I'm going to modify it. I had some time to think this through, but not exactly to work out. So I hope I'm modifying it the correct way. And I think the way to modify it is this way. I'm going to add a capacitor in parallel with the inductor. So it's either parallel or series. And I think a series actually makes it worse. I think. So let me do it parallel, and if it doesn't work, then I'll go back and do a series. So when I add an inductor in parallel, then not inductor, capacitor in parallel to the inductor, then this is now what I have to do. So let me erase all this. I'm just gonna rewrite it with the modified version. Yeah, so the impedance of the capacitor is given by 1/I omega C. I tried to write it so that my C is not confusing compared to L. And I analyzed this like any 3-register circuit where 2 of them are parallel and 1 of them is in series to that parallel thing. So I will need to add these first to get my, let's label it G1. So my G1 is going to be computed this way. 1/G1 is equal to 1/GL plus 1/GC. Or let me write it all in, 1/I omega L plus reciprocal of that, I omega C. Let me try to combine these two. Factor out I, so omega C. And then factoring out I from here should give me -1, minus 1/omega L. And if I wanted to simplify this a little bit more, it'll look like I times omega squared LC. That's this term multiplied up and down by omega L minus this numerator here, 1, divided by omega L. Okay, so that's my, or the reciprocal of that. So my G1 is minus I omega L divided by omega squared LC minus 1. And this quantity has certain properties. Let me just highlight some of those properties. It's a frequency dependent. So if you imagine a regime where frequency of your circuit is very low, so that the impedance of the inductor is low and impedance of capacitor is high, then this combination should look kind of more or less like impedance of inductor. And if you imagine omega approaching 0, then this omega squared in the denominator goes to 0 more quickly. The denominator kind of looks like a minus 1. Minus cancels that, so G1 kind of, before it completely goes to 0, it goes to I omega L, which is sort of what you'd expect. And you know, if you imagine where this goes to high frequency, so that the impedance of inductor is very high and the impedance of capacitor is very low, then if you work out all the math, G of 1 should go like 1 over I omega C, again, before it completely goes to 0. This quantity is a very special property. As omega goes to 1 over LC square rooted, as in when this combination of factors approaches 1, G of 1 approaches infinity. It looks like an open circuit here. In some sense, inductor and capacitor cancel each other out. And you know, when you are installing capacitor here for a particular purpose in mind, actually this frequency will be your operating frequency. Or rather, I guess you pick your capacitance values so that this condition is true at your operating frequency, precisely with the intent of making G1 approach infinity, or make it infinity. So with this modification, my equivalent impedance is equal to, so I'm just going to use G1 as an expression. It's going to be my, no. Let me say this quantity here is minus I G1. So when I use the letter G1, it'll be simply referring to this combination here, which is real. So my equivalent impedance of this whole thing is going to be the impedance of the resistor, R, plus the impedance of this combination, which is minus Ig1. And with that complex impedance, the current through the circuit will be the applied voltage, complex, divided by the equivalent impedance. Or if I'm interested in just time average of the current squared, then the way you would calculate it is this way. You calculate it by the complex conjugate of VT divided by G complex conjugate of the equivalent resistance times the original thing divided by G equivalence. And the numerator portion is simply going to give me V naught squared over 2. That's the calculation I've done a few times now. That's what I'm going to get. Divided by, and this calculation, G complex conjugate times G itself, is going to give me, let me do it on the side here. It's R plus IG1. This is why I wanted to define G1 as positive or real, times, it doesn't matter if it's positive or negative, R minus IG1. And when you go through the algebra here, what you are going to get is R squared plus G1 squared. So my average I squared is R squared plus G1 squared. And this is what I want you to see. Under this condition, G1, the real value, or the absolute value of G1 goes to infinity. so when this condition holds, what you're going to see for this current flow out of the power source, current or the average power squared or average of current squared is going to go to zero. Meaning, when I do this power dissipated in resistor calculation and multiply it by resistance, this is going to be vanishingly small. There will be much less current flowing through the resistor, and very little power will be wasted in the resistor here. And so then you might ask, then doesn't that simply mean this inductive load or motor is not receiving as much? So if average current power out of the power supply is zero, then how does this work? If you repeat the analysis for not the total current, but simply for the current through the inductor, then you will find that the I squared value of this is not actually approaching zero. And what you basically have is there's a circulating current here. Current kind of circulates between capacitor and inductor. And this current never has to cross this resistor, so it doesn't waste any power. And this is the principle or reason behind the power factor correction. That if you have an inductive load, we are used to saying large inductive load. And I think by large inductive load, we really mean a kind of inductive load that would draw large current. So, and that usually sometimes it actually means low L. So if you have a large inductive load, a kind of inductive load that would draw large current, without this corrective capacitor here, a lot of the current will be forced to go through, let's say, resistance of power transmission line, and you'll be wasting a lot of power. And it's power efficient to correct that. The way is install a capacitor bank near the inductors or near the motors, or if it's a smaller device, sometimes these corrective capacitors are just built into the device, and that limits the amount of current that flows on the main branch while preserving the current that does need to flow through the inductor for it to do whatever it is it does. If it's a motor, spin. So this is one of the things that electrical engineers figure out. And with the use of complex impedances, some of the considerations that go into that is something that we can work out for ourselves with the use of impedances and the knowledge that power is only dissipated in the resistor. So even though there's large current flowing through the inductor and capacitor, those we don't worry about because no power is dissipated in the inductor and capacitor.